Okay, so second presentation. So here I will show you some experimental results of our INSTRA and LD Lensrod project. So INSTRA was a national project, but it's the basis for this LD Lensrod study. So I start with this INSTRA because we have some more data about this project at the moment. So it's again whole body irradiation with this cobalt source, and here we just use the low dose rate of 0.063 gray per minute and low doses for the irradiation from 0.063 gray to a maximum 0.5 gray. And this maximum dose we choose because in old literature, this was the dose where clearly cataracts were seen in mice, so it was different mouse strains and so on. But that's the reason why we choose this 0.5 gray. Should be a positive control. But okay, let's see. So we have male and female mice. So from a wild type strain, Black 6 C3H heterozygous mice, because our mutant, the ERCC2 heterozygous mutants, which are healthy in their phenotype, the heterozygous ones, but these were on a C3H background, and maybe you know C3H mice develop a retinopathy, and that's why we use these F1 mice. So they are healthy. And we implemented also these in vivo experiments here, and these cohorts were examined up to 24 months after irradiation. Irradiation time point was again 10 weeks of age. And we used Scheimpflug technique to look for the lens opacity, and also used OCT, optical coherence tomography, to look for retinal degenerations or retinal changes. So it's not much reported about retinal changes, especially at lower doses, but okay, if we have this cohort, we want to look for this. And we did behavior experiments to look for cognitive effects at 3 different time points, 4, 12, and 18 months after irradiation. And have different dissection and organ sampling time points. So 2 early ones, 4 and 24 hours after irradiation, 4, 12, 18, and 24 months after irradiation for organ collection and so on. And yeah, I think you know how Scheimpflug imaging works. So usually it's used for humans. We have Oculus Pentacam, and it can be also used for mice. So you just have to grab them tightly in your hand and hold in front of the machine, and then you get these Scheimpflug pictures. And also the same for the OCT. It's a machine usually used for humans, as you can see here. But for this examination, we have to anesthetize the mice. You can't hold them that fixed for this. It's too long. And what we did here, we had a look at the retinal fundus and the different retinal layers, and analyzed the retinal thickness. So these are some examples of Scheimpflug pictures from mice 24 months after irradiation from Schem irradiated mouse and 0.5 gray irradiated mouse. You immediately can see, so there's not much difference. So this bright spot is a reflection. It's typical in the front, so you shouldn't measure this one. And the only thing is 24 months after irradiation, you see this more shiny ring in lens nucleus. And again, you can see even after 24 months, the difference between all the groups of different doses and unirradiated mice are not really different. And so the maximal lens density is here about 8%. And but finally, so when we did statistics of the data, we could find a sex effect and no mutation effect in our CC2 heterozygous mice. And we have a clear, significant dose effect, but again, it's not really clinically relevant, because usually you have this clinical relevance usually is defined here. So I put the definition. So it comes from humans. So visual acuity starts at lens density of more than 10, so 14% lens density. But a very good thing of this Scheimpflug system is you really get quantitative data in comparison to slit lamp, where you mostly don't even have a picture, so you can do it, but usually it's not done. And so the classification somehow is subjective, so every person will do a bit different. And so for the Scheimpflug system, you really have quantitative data that's really good. It's not that observer dependent. And yeah, for what we want to check for, because it's always said ionizing radiation causes posterior subcapsular cataracts, but here one of recent study from Asisova et al. Shows even in humans, so these are humans from this Maya cohort, I think you all have heard from, shows that the main type of cataract is posterior subcapsular cataracts, but they also found a lot of cortical cataracts and nuclear cataracts. So what we were not quite sure if we really could see posterior subcapsular cataracts in mice, because mice have a much bigger lens compared to human lens. And that's another thing we wanted to check, if Scheimpflug imaging is really suitable for mice. So these are some example pictures. So this is an ERCC2 homozygous mouse. So in a homozygous status, ERCC2 mice really get cataracts, but not in the heterozygous state. Then these mice are healthy. So this is 0.5 gray irradiated mouse, 24 months after irradiation. And this also. So here you can nicely see the anterior clouding in the lens, and also some shiny thing in the back of the eye. And so this is these are the histological sections of this eye, and you can clearly see anterior and posterior changes. And yeah, this is another example, also 0.5 gray irradiated mouse, 24 months after irradiation. Here you have a clear posterior subcapsular cataract and clear changes of the lens fiber structure in the histology, but in the Scheimpflug, I'm not sure. We didn't realize this might be a different shiny thing of a wild type, but you can't clearly see this posterior cataract. What you can see here is change in the cornea. So we often see this 24 months after irradiation. So, but it's an age-dependent effect. And to check, especially for the posterior subcapsular cataracts, we did histological sections of all eyes from irradiated mice we had, and checked the histological sections for disturbances of the lens structure. So this is an example always without some findings in the anterior part, the lens bow region, and the posterior part. And here we have some enlarged and swollen cells and some small vacuoles. Here, these are really big swollen cells here with the stars, and also here in the posterior part we found enlarged cells, and here it's also seen a kind of detachment of the lens epithelial cells. What we found here, so mislocated cell nuclei, usually during lens development, the epithelial cells move to the interior part of the lens, and the cell nuclei are degraded, and usually you can't find cell nuclei under this lens bow region. So, but here some cell nuclei moved downwards. Maybe here in the back of the eye, we found also some mislocated cell nuclei still present in the lens. It's not normal, and these things are more really classified as cataracts with swollen cells and open parts. And we try to classify all these changes in the histology of the lenses, and this is still an ongoing analysis. So we analyzed 10 to 12 eyes per dose group and classified all the morphological changes at different time points, 12, 18, and 24 months after irradiation. And so what we can say at the moment, so that's a preliminary statistics, at the moment shows a really significant radiation effect for the posterior subcapsular cataracts, visible in the morphological picture, so in the histology, for the dose group of 0.5 gray. So odds ratio is 13.8 here. And back. And I said we also did this OCT examination of the retinal fundus layers and retinal thickness. So this is results from this first project, so the INSTRA project, so for the retinal fundus and the main vessels visible in the fundus. We couldn't find any changes, not between wild-type and mutant mice, and also between irradiated and not irradiated mice. But so after 20 months after irradiation, also 24 months after irradiation, we had slightly thinner retina in the irradiated group compared to 0.5 gray irradiated group compared to the wild types. So, but it's really low but significant. And we were not sure what does it mean, but maybe later from LD lens rod experiments, it's clear it seems to be real. So yeah, then let's come to the HMDU from Helmholtz Center Munich, part of the LD Lensrad project. So the whole project I introduced you all to already. So we irradiated the mice nearly the same, so under the same cobalt source we used for the INSTRA project. So, but here we used the higher dose rate of 0.3 gray per minute, and doses applied are 0.5 gray, 1 and 2 gray. And here we added an additional mouse group where we did the irradiation not 10 weeks after at the age of 10 weeks, but in neonatals, so in 2 days after birth. But first let me present the data of 10-week-old irradiated mice. So this Scheimpflug data of the wild type and the mutant mice. So as I showed you before, so they are not clinically relevant differences between the groups in lens density, even if the two-way ANOVA shows aligned dose significance for these mice, but it's, yeah, if not clinically relevant, yeah, maybe it's not that important. But you can clearly see a dose effect. So there is a dose effect. And we, as I said, we want to look for the Scheimpflug imaging if we see really the posterior part of the lens. So from histological pictures in some where we found posterior cataracts in the histology, we couldn't see in the Scheimpflug imaging. And now we have a new OCT machine where you really can nicely go through the whole eye. So where you can image the cornea, the anterior part of the lens, and in this example, the posterior part of the lens. And so this is the same mouse eye from a 1 gray irradiated mouse 15 months after irradiation. And in Scheimpflug imaging, yeah, can't be sure, so there's some clouding of the lens, because so the data you get when you measure the lens density with this Scheimpflug machine, so it's not really different from wild type. And but here in the OCT machine, you really can see these lens lesions in the posterior part of the lens. So what's not that nice, you can't quantify this, but it's visible. And so you can even have some kind of sections, virtual sections through the posterior part of the lens, as you see here. And here you see this part always pops up, so where it's clear and you have some kind of cataract. This is a mouse 18 months after irradiation. And now we try to quantify the mice with the OCT, so where we found something in the posterior part of the lens. So the posterior changes are marked in blue here, and this is 0 gray, so sham irradiated mice on the top, and the 0.5 gray irradiated mice on this panel down here. And you see the blue part is increased, and so that means we have much more posterior lesions in these 0.5 gray irradiated mice. And we did the lens histology, or mainly our PhD student Daniel Pavlicek. And here in the histological pictures of some examples, you can find these, what is, this, he calls always the signal-free plane in the OCT examination. So, and this correlates very good with these swollen parts of these cells. And he tries to quantify this part and correlate with the OCT, and he's really hard working on this. We don't know if this will really work out, but he tries to find a method how to quantify these OCT lesions. And what he did, so his first quantification of these regions you can see here. So it's unirradiated wild-type males, females. I think you can't read it. Mutant males, mutant females, and these are 0.5 gray irradiated mice. And you see they show much more lesions in the posterior part of the lens with the OCT method, and even more with after 1 gray irradiation and 2 gray irradiation. So it looks like the posterior subcapsular cataracts really are dose dependent. So, but it's ongoing experiments. It's not finished and at the moment, so it's quantification put to a different scheme. So here we have 19 months after irradiation. For the 2 grades, just 15, so it's ongoing, as I said, but compared to the unirradiated mice, so we have all groups show significant differences to unirradiated mice for the posterior cataracts. And what he also did is to measure the retinal thickness also with the OCT method, as I showed you before for the INSTRA project, and here in wild type and mutant mice. But you see finally it's not that big difference. And he found some differences for male and female here in the wild type mice, but not with the 0.5 and 1 gray irradiation. For the 2 grays, we don't have data at the moment. And here comes this additional mouse group, so where we irradiated neonatal mice. So there is hint, so age is a very important factor for the development of cataracts. Here it's came from Gajewski et al. So where he showed that mice are most susceptible to ionizing radiation at up to 5 days of age, and this is data from INEA, so from the paper of De Stefano. And here again we have these patched mice, and so also irradiated at the age of 2 days, and we have a big increase of cataracts in these early irradiated mice. So we don't see this, or they don't see this in the here 10 days and 56 days irradiated mice. So these are here. But let's come to our 2 neonatal irradiated mice. So these are again these OCT pictures of wild type and mutant mice, sham irradiated and 2 gray irradiated mice. So this is a normal mouse. lens, and here you can see this cortical cataract is developing, and here is also nuclear cortical and some kind of posterior cataracts, and so this looks like even not the lens is somehow leaky, and we could see this also in histological pictures afterwards. And especially for the cortical cataracts, so after we just irradiated with 2-gray these neonatal mice, and we found in nearly all of them some clouding in the lens. And what we found also is the retinal analysis shows different layers or difference in the retinal layers after 2-gray irradiation at P2. So you can see this in OCT picture already. So that here in the IS and OS, so the inner and outer segments of the photoreceptor cells are thinner or nearly missing, and here in the histological picture you can clearly see this, that the photoreceptor cells are diminished, so compared to a sham irradiated mouse. And yeah, it's can be clearly seen here in these graphs. So the retina is clearly disturbed and is much thinner. So let's come to the conclusion we can draw up to now. So the cohorts of mice after 0.5 and higher doses show a slight but dose-dependent increase in lens opacity. It's not clinically relevant, as I said, but it's significant. So our mutant mice didn't show a higher susceptibility to ionizing radiation. And but the age of irradiation for the mice, it's really crucial for the alterations in the eyes. So we saw big alterations in these mice in the lens and the retina. So maybe the retina is not that radiation resistant as thought sometimes. And so, and also it's important which method you should choose for the examination of your mice. So thank you to all people who contributed to these results, Instra and LD Lensrad, and thank you for listening.
David Simar, University of New South Wales in Australia. Thank you, that was a very interesting talk. And I must apologize because this is really not my expertise, but I'm pretty fascinated by the difference that you find in terms of neonatal versus adult mice. And could you actually speculate on why you think that they are more sensitive earlier in life?
Maybe because especially for the lens. It's still a developmental stage of the mice. So the lens is not fully developed. So it might be that DNA damage causes more damage to the lens in this state because the lens is still developed, and so that might cause,
In addition to DNA damage, have you ever thought about the potential contribution of epigenetic mechanisms as well? A reprogramming of stem cells, for instance, that could actually be carried forward during life?
This might be an idea, but it's still an ongoing experiment, and we don't have results about the mechanistics at the moment. So these mice are still alive, but we will collect eyes and organs soon, and yeah, we will do more experiments with these organs for sure. But at the moment, I can't say anything about this.
Thank you.
Welcome.
Thank you, David. Merci, David. French are everywhere, even in Australia. Do we have other questions? Laurence.
Laurence Roy from the RSN France. I don't know whether I understood properly, but you showed an age effect, and I understood that you only have 2% increase with age. It was surprising to me because it is quite low. Or
no, yeah, right. Just statistically, so the age effect for the higher lens densities is about 2%, while the radiation effect is lower and it's about 1%. So the aging causes much more damage to the lens than this 0.5 gray irradiation. So these were data from this first project, from the INSTA project, yeah.
Yes, we have a question from Rafi and then from you.
Yeah, it's the question going in the same sense of aging, even for the let's say the P2 irradiation, you see less effects with the irradiation than with the normal aging?
For the P2 mice, it seems not to be true. So because in the P2 mice you have these strong radiation effects, you really see these dense lenses, and also you can see in the Scheimpflug examination. So you also have big differences in the lens density in these P2 irradiated mice.
Okay, thank you.
Alex Zorgakillas from NTUA in Athens, Greece. Mm-hmm. So, do you observe any effects on non-irradiated areas?
Pardon?
Do you observe any effects on non-irradiated areas?
Non-irradiated areas, I think we don't have. So it's a whole body irradiation, and the whole eye should be irradiated. Maybe at different doses, so might be that the back part is less irradiated, but I don't think so. Mouse eyes are really small, so...
Yeah, it's whole.
Olga Martin from University of Melbourne. I just have a remark about DNA damage response in young and old mice. We had a study with our colleagues in Canada, and we have shown that, yes, there is a dramatic difference between response of neonatal mice and older and old mice as well. So neonatal mice have a very good recognition of DNA damage and very good repair, while old mice don't recognize DNA damage very well, and repair is very slow. So similarly, there are differences between wild-type mice and mice with defects in DNA repair. So the same thing for mice with defects in DNA repair is the lower recognition of DNA damage and slower repair. So it might be helpful in explanation of your data.
Mm-hmm. With the younger mice, so we couldn't examine DNA damage at the moment, but so that's really interesting what you said. Thank you.